Now we have discussed the trigonometric Fourier series. Now we are going to discuss about the complex form of the Fourier series. This complex form of the Fourier series is also called as the exponential Fourier series. Exponential Fourier series. So we know that according to the Euler's identity, e raised to j theta is equal to cos theta plus j sine theta. So it means exponential signal can be represented in terms of sine and cos, or sine and cos can also be represented using exponential signal. Both trigonometric and the exponential are same. Here the same formula is converted to the exponential Fourier series. In terms of this exponential Fourier series, there is no a0, an and the bn coefficient. Only there is one coefficient is present. This is called as the cn, and that cn is called as the exponential Fourier series coefficient. And this exponential Fourier series is given by x of t is equal to n is equal to minus infinity to infinity. And in previous case trigonometric, the limit was from 1 to infinity. So cn e raised to j, here it is a plus e raised to j n omega 0 t. So once if you find out the cn, you substitute the values of the cn, and that signal is called as the exponential Fourier series. And the value of cn, which is called as the Fourier series coefficient, is given by 1 upon capital T. The integration for the one period x of t e raised to minus j n omega 0 t dt. The procedure is same. You find out the value of capital T. From that, find out the omega 0. Then represent the signal x of t for the one period in terms of the mathematical equation, and you calculate the cn, and from the cn you can write this exponential Fourier series equation. All are same, and accordingly if you compare this the trigonometric and the exponential Fourier series, so here the c0 is equal to your a0, cn is equal to 1 upon 2 an minus jbn, and c minus n is equal to 1 upon 2 an plus the jbn will be there, which is the complex conjugate of each other. And accordingly, if x is real, accordingly this you can find out the magnitude and the phase value. Mod of this cn is called as the magnitude, and d raised to j theta n is called as the phase. And you calculate this theta pi n, tan inverse of the minus bn by an, where the bn is imaginary part of the signal and an is the real part of the signal. And from this an and bn, you can calculate the magnitude spectrum and the phase spectrum. The magnitude spectrum is that spectrum which is the graph with respect to the magnitude with respect to the frequencies, and the phase is, it is a graph of the frequencies with respect to phase, and phase and magnitude you can calculate from the cn. Another one of the important thing about this Fourier series is about the Parseval's relation, because the power of the signal is important. So you can find out the power in the time domain. Similarly, by using Fourier series, you can also find out the power, and that relationship is called as the Parseval's relation. This Parseval's relation you can represent by using this is a power of the signal in the time domain is given by this x of t square into the dt. The same power you can find out in the frequency domain, and that is given by this relationship, which is called as the Parseval's relationship. Power is equal to n is equal to minus infinity to infinity mod of cn square. So Parseval's relationship, it gives the power relationship of the frequency domain, the signal. So using Fourier series coefficient, you can calculate power of the signal. And this is same Parseval's relation, power in the time domain, and this is the power in the frequency domain, which is called as the Parseval's relationship. So another thing about the spectrum of the signal. So if you plot the magnitude spectrum, so this is a mod of cn is called as the magnitude, which is under root of 1 by 2 an square plus bn square. So you can calculate the magnitude with respect to the frequencies, and this because we know that Fourier series is accurate representation of the signal x of t in terms of sinusoidal signal with fundamental and harmonic. So the spectrum is present only for the fundamental and harmonic signal. So the spectrum of the nature in case of the Fourier series is discrete in nature, you keep in mind. It is discrete in nature. So the graph of magnitude with respect to frequency is called as the amplitude spectrum. The graph of the phase with respect to frequency is called as the phase spectrum. So this amplitude spectrum is the even function. It is always even. So it is symmetric with respect to the y-axis, and this is the anti-symmetric with respect to the y-axis, that you remember. So you can find out the Cn, you can find out the C0, you can find out this phi n, which is called as the angle, and for different values of the n, calculate the values of the Cn and the phi n, and you can able to sketch amplitude and the phase spectrum. So now let us take such kind of the problem here. You already found the trigonometric Fourier series, and the same you can find out the exponential Fourier series. So first you calculate that, you write the x of t. For this, calculate the capital T. From that you calculate the omega 0, and you calculate the exponential Fourier series, that is your the Cn. So just here the solution is given, you can go through it and you can find out. And generally, so if you see the rectangular signal, the Fourier series of this rectangular is a sinc function, and you can convert this into the form of the sinc. It is solved problem, you can go through it, and accordingly you can sketch the amplitude and the phase spectrum of such kind of the signals, which is shown here. This is another signal. The same way you can find out the exponential Fourier series. Okay, the solution is the given here. So this is end of the Fourier series, trigonometric and the exponential Fourier series.